The photograph in the background of this whole slide deck is the view from the 213 J&K plutonium vaults embedded in Gable Mountain at Hanford. Photographer Arthur S. Aubrey and I called this photo the road to Los Alamos. The image shows the road that the first shipments of plutonium nitrate paste took on board the trucks that Major Joseph Sally outfitted for that journey. In Sally's memo to Major Sapper of 26 January 1945, Sally listed the requirements of these shipments. There's the vault itself. Among the items Sally required were one radio for the 213 vault, one radio for the escort car, one radio for the 3/4-ton truck, 12 masks, 12 pair of gloves. And that's it for the list of what you needed to drive plutonium destined for an atomic weapon on public roads from Hanford to Los Alamos in 1945. I would like to thank Dean Catherine Banks, Mr. Mark Triplett, and Professor Robert Franklin, along with their team members across the 4 respective colleges and universities, for inviting me to the 2024 Hanford Nuclear Legacy Series. Let me say a few words at the outset about this talk and how I've structured it. I've prepared a paper because I'm an egghead academic and that's what we do. However, there is a slide deck, and the slide deck that you'll see here projected on the screens. However, I'm not going to read you the text from the slides. You can do a better job of that than I can. The paper is loosely synced up with the slide deck. It's more like a documentary film with a voiceover, but one that doesn't have quite the budget or the talent of a Ken Burns PBS series. I'll forgive you if you walked into this lecture mesmerized by the chalk dust of the physicist's blackboard calculations from the early days of the Manhattan Project, and that is if you happen to have seen the movie Oppenheimer. Hanford, in the film Oppenheimer, is relegated to a glass jar. As the movie advances, through time, the glass jar incrementally fills with marbles. The marbles represent Hanford's plutonium production of metal. Behind these scenes, behind the chalkboards, it was Hanford that produced the plutonium for the first nuclear detonation, July of 1945. Hanford was an industrial story of the Manhattan Project, especially if we follow the work of historian Bruce Heavley, who in his scholarship has noted that the Manhattan Project was, at its core, a massive industrial undertaking. Let's cue evidence from the historical record. Julius Robert Oppenheimer, on Tuesday, 5 June, 1945, was frantically calling on an open phone line from his office in Los Alamos, Major Joseph F. Sally at Hanford. Sally, chief of production at Hanford, in his office diary recalls this phone call in language that indicates an ease and familiarity in their relationship, not found in the better-known diaries of Colonel Matthias and his recollections of discussions with Oppenheimer. Sally was born in 1913. Oppenheimer was born 11 years earlier in 1904. Both Sally and Oppenheimer were non-observant Jewish New Yorkers. Each of them attended elite New York City high schools and Ivy League universities. Do you believe that Sally thought that he would actually end up out here when he was at Stuyvesant High School that became famous later, Teacher Man, in that book, Teacher Man, that it just such a world away from New York City. There's Sally right there. Sally was among the first in America to earn a degree in chemical engineering. doing so in 1936 from Cornell, while Oppenheimer pursued studies in physics from Harvard and then in Europe. In his phone call to Sally on the 5th of June, 41 days before the Trinity test, on July 16th, 1945, first use of an atomic bomb, Oppenheimer wanted to know the concentration of product in cans 36 to 41. Of this call, Sally wrote in his office diary that he suggested Mr. Oppenheimer, quote, look further within his own organization as this information appears on the shipping documents. Oppenheimer stated that he did not know this and that if we did not hear further that afternoon, that we might consider that he had the necessary information. We never heard from him again. Historian Richard White has called the Columbia River the organic machine. He has an engaging chapter on Hanford. With the Columbia River in mind, we might consider that the intersection of chemical engineering and the Columbia River may get us closer to the heart of this story. Decades before Hanford caught the eye of Colonel Matthias in his scouting missions, December of 42, an entire network of non-ferrous metal smelters populated the American West, linked by the Milwaukee rail line. The aluminum smelters in particular needed massive amounts of electricity to convert bauxite into aluminum metal. Chemical engineers designed and operated these smelters. Other engineers designed the hydroelectric dams these aluminum smelters were co-located with along the Columbia. Together, chemical engineers and the energy of the Columbia made dramatic impacts on the environment that remain with us today in the Columbia Basin. One could say that chemical engineers moderated the environment. Moderated in the sense of arbitrating the development of the Columbia Basin. In the case of Major Joseph Sally, his chemical engineering exploits involved another form of moderation, to slow down neutrons during fission so that they are harnessed in turn to create controlled fission in a reactor. In the early 1940s, the US was exploring two methods of moderating neutrons, heavy water and graphite. They put Major Joseph Sally in charge of the chemical engineering of both methods. Sally's heavy water project took place near the headwaters of the Columbia River near Trail, British Columbia, Canada. Sally's graphite project took place further down the Columbia at a little place called Hanford. Sally must have been, and he must have made an impression on the higher-ups because once he built the heavy water plant at Trail, they had him continue to manage its operations and sent him to Hanford to oversee plutonium production. He commuted to Trail on the weekends. All the while, the Columbia River rolls along, providing energy for Sally's exploits and room for us to consider scholar Gabriel Hecht's idea of nuclearity along these lines. Nuclearity for Hecht illustrates how places, objects, or hazards get designated as nuclear. Hecht's scholarship in Being Nuclear from 2012 does important work critically unpacking the front side of the nuclear global industry, mining and milling of uranium. In Residual Governance 2023, Hecht continues her path-breaking work by linking questions of health, safety, and the environment to the regulating and the failure to adequately regulate wastes and exposures to wastes stemming from mining industries. Here I emphasize the historical significance of materials overlooked by historians once designated unnuclear, such as chemicals used in the separation process to extract plutonium from used reactor fuel at Hanford. Midway Substation. Industrial plants require massive amounts of electricity. One could argue that we are here at this location today discussing Hanford because the BPA's Midway Substation was regulating electricity from Grand Coulee and Bonneville dams in 1941. A year before the Manhattan Project scouting missions for an official missions in the area. Arthur S. Aubrey's photograph of Midway Substation could be mistaken for an official government document. He shot this in 1999. Aubrey uses a high modernist aesthetic that matches the architectural design of the building and allows us to feel modernism as we view a substation that is mundane in another location. Thinking about nuclearity in another way, we might think about life cycle concepts found in global sustainability standards in its concern with the chemical reduction of metals that contributed to the U.S. military arsenal, plutonium among them. The reduction and purification of metal is a specific industrial process phase that allows comparisons across industries and hazards, emphasizing the step that often generates the greatest environmental impacts, of which we'll learn about in some detail from Bruce Napier coming up. This includes the chemical processing of uranium and its byproducts, including plutonium and associated wastes, along with other non-ferrous metals such as lead, copper, and zinc. In exploring the implications of how nuclearity may be applied more broadly and across other industries, the idea may become a critical method and act as a starting point to help us explain what gets lost historically. Nuclearity may help us recover linkages between hazards and industrial sites wherein some locations are designated nuclear and others remain generically industrial. More often characterized by chemical contaminants or the residuals of non-ferrous metal smelting rather than radiological ones. Let us now turn our attention to the nuts and bolts of smelting plutonium. Here we go with the map of the Hanford site, and we're going to be focused right here, right in this area, right there, on the plateau area, as it's called. So T-plant, and we heard some discussion earlier about T-plant, and we will see in some detail the after effects of releasing emissions out the stack at T-plant in particular in Bruce's talk that's coming up. T-plant was the first Hanford smelter to go online. It used a batch process. U-plant was kept in reserve as a backup. Later on, is an interesting side note, U-plant was actually the site of a massive underground mining operation to recover uranium in the bottom of tanks. It was a sluice mining operation, and it was retrofitted to essentially stockpile uranium that was sent to tanks as a waste product. And that ended up in armor-piercing shells and in the armor of tanks from the bottom of the tanks at Hanford. The first generation of smelters were originally bismuth phosphate batch process to reduce plutonium metal. The second generation used hexone methyl isobutyl ketone in a gravity-fed solvent extraction columns. The process took place at a facility, this is at the height of the secrecy of the Cold War, called redox. The process was called redox. That was a real kind of a moment of real insight into secrecy there at Hanford, to name the super secret second generation of solvent extraction, right, because the idea was it was right out in front, right out in cover. So redox is the facility, redox is the super secret new process that they're going to use. Purex, as we've heard, the workhorse, right, that was restarted by Reagan. Well, it uses tributyl phosphate as a primary chemical solvent. And here you can see that in tying in with our 5-year project here with a consortium of universities, I've tried to link in that we have a use of Purex significantly in Japan, and they have successfully reprocessed about 50 tons of uranium. So they're actually approximating the Hanford, they're under it, but they're approximating the actual loadout of plutonium metal at Hanford. But it's civilian plutonium, and they've signed a non-proliferation treaty. I'll go into that at the end of the slide deck here. So now we're going to start on our journey. We have a little journey we're going to take. Who here remembers or has ever been on a little bit of a train ride when you were a kid, on a little train, those smaller trains you could sit on and ride? It's kind of a similar thing, excepting you wouldn't really want to sit on this cast car. It was this cast car, and the rolling stock here, would start out in the reactor areas, and it would be fed out of the rear face of the reactor. It's the feedstock for chemical separations, and sent to a staging facility at Hanford. This building here, you could argue, it seems innocuous, doesn't it? Maybe not. You could argue that decisions made concerning the use of this building had some of the most significant impacts on off-site public health in Hanford history. This building is where irradiated fuel was stored after the reactors and before smelting. It's the leg storage facility. It's another Aubrey photograph. They didn't call these things Queen Mary's for nothing. They're just massive facilities. So the nickname of the Queen Mary, Aubrey uses some perspective here to give us a sense of the massiveness. He overdoes it here, and I think he's quite aware of that. But he's giving us a sense of the largesse of the facility. They varied, the canyons did, to some extent in length, but plus 800 feet in most cases. Okay, now we are over on to the photography of interiors. What we're trying to do here in this session is give you some background into what the chemical processing itself was really like at Hanford, so that you have some, we're kind of in between the first session talking about Cold War, a lot of policy aspects, social impacts, and the actual emissions themselves that Bruce is going to talk about. To understand that, really, Professor Franklin talked about and it's interesting, in Hanford history, there's kind of a gray zone of a ton of technical information, And getting your mind around that's challenging. However, I want to try to simplify that for us so that everyone should be able to understand what went on here, because most people can get their mind around a smelting plant that makes iron. And that's really what happened here, except it was a wet process. It's like how they make zinc. It's hydrometallurgical smelting. There's 3 types of smelting. So that's really what's happening. In the case of this slide, what we're looking at here, we're bringing you into chemical processing, okay? There was a cutaway, and there still is. I'm not sure if you could get in there anymore. This was in the late 90s, but there's a project where they were looking at, I have some slides on this in a moment, but they were looking at ways to potentially entomb this facility through a project called the Canyon Disposition Initiative. So they allowed people like myself, some others, government-funded history work to get inside this location, normally off limits. One of the probably, of all of the facilities, it's the only canyon deck you could walk on for even a little bit of time, because there wasn't direct plutonium processing in this facility. You're talking about uranium waste recovery in the sluice mining. So one thing you can notice here, you can notice this tank right there. Can you see what's written on this tank? It says it's a dissolver tank. So inside of these cells, these are below grade. Here you have the crane hooks, and there is a gantry crane that goes down and back, and there's a crane operator up in there. I tried to get him to wave, but he wouldn't really lean his head down. The crane will lift up these hooks, and underneath you'll have tanks such as a dissolver tank. And one of the key components, now Bruce can clarify this because he's more of an expert on this than I am, but I can tell you, I can set him up by saying that in the sense of dissolver tanks, irradiated fuel, you remember the little cast car that we had, the lead-lined cast car, right? A crane operator, and imagine that dissolver tank is inside a process cell down below grade. They've lifted the block off of the process cell, and they have dumped the irradiated fuel assemblies into the dissolver tank. Now, the first step that happens is a decladding, because at the time, there was aluminum and material for another totally geeky talk would be the molten metal dipping that went on to actually preserve the uranium itself, which is super complicated and actually very fascinating, that Sally had a huge hand in actually resolving, believe it or not, back in 1945. That's a part of my book that'll be forthcoming. He actually sent 15 tons of, Sally sent 15 tons of contaminated tin up to Trail to have resmelted, because tin was critical, just as critical almost as uranium, for eliminating corrosion of the uranium itself while inside a reactor. And so the tin, which they hadn't anticipated, was becoming contaminated because it was molten, and it was in the dipping process itself that Sally realized, we've got a real problem, Houston. We've got a major problem. And so Sally's recognition of that is a key reason that the Trinity test even happened. And you're hearing this first here today because his diaries have not been published on or dealt with to this point. After the decladding, we have a use of nitric acid to create a slurry. Right, Bruce? We need a slurry. See, he's nodding. We cannot have physical chunks of irradiated uranium going through these canyons. It won't work. So have any of you ever taken a garden hose and put a little fertilizer bottle on it? Has anyone ever done that? Okay. You can then understand how Hanford operated, because it operated on steam jetting. Anytime you take a high pressure, in this case water, and force it over an orifice, and it pulls that out along with it, that's a jet. There's a jet that's up in the air, but steam jetting is how all of this worked. You know, the steam plant out there, it was absolutely critical for these activities. So if you take irradiated uranium slugs and you've taken the cladding off of them, and then you say, I want a slurry, because you're a crazed industrial chemical engineer, and you just got to jet this stuff down and get it into centrifuges, that's what you're going to do. And so nitric acid is your key there. Well, here we go. This is probably one of your ultimate photos of an operator at Hanford. This is the B plant's concentration facility. This is where you're talking about taking plutonium nitrate paste and moving it into a further state of concentration and getting it close enough, especially in the early days, to where you could load it out in a toothpaste-like consistency at that point in time. So a couple of things here, just to get into the weeds, because I kind of like that. You're talking about the skimmer right there. That's a centrifuge tool. You're looking at the plow, and you've got the sparger. A sparger is going to add, this is a centrifuge working station. So you can control the speeds here, right there, on and off. And these wheels, you're going to be removing plutonium from the actual side of the centrifuge during the process at a certain point. So all of these are, and here you have an actual jet, and you can see that the jet is set from one cell to another. You see that? The jetting moves the material through steam jetting. Here is an example of, we think of Hanford as, and it's very fair, some of the first concerned reactors, and it's completely understandable. However, if you could argue a bulk of the operational energy and the intricacy and piping and effort level and dollars spent, it dwarfs anything else in terms of chemical processing. Here's an example of how industrial and chemically oriented Hanford is. These are tanks and redox, and each one of these tanks has a very specific function in reducing irradiated uranium to the tiny bit of that is plutonium metal. It's a reduction just like iron ore or zinc ore or aluminum or bauxite, anything like that. So, what do we do with the smelters now? What should we do with them? Here's one idea. Put it inside a tomb. Bury it. How would we know where things were or what was there if we were to do this? That's an open question. What is the role of landscape and the industrial architecture in helping orient us to what we have created in the past, and how will future generations orient themselves to this? Has anyone ever been to Gasworks Park in Seattle? They've left all of the industrial architecture up. There's certainly multiple ways to look at that. But in this notion here, and it's only one of several options that are explained, as a sidebar, I would, if you're interested in some light reading some evening, the Nez Perce Engineering Group has a fascinating set of comments on this idea. And they note in their comments that they are training the next generations of engineers to handle some of the information that they're not totally sure is going to be tracked on. Very interesting. One alternative way to look at this is to consider the role of art in understanding. Here's something that an artist, Warren Dykman, it's called Reactor 2. He went to Kennewick, finished his work at Kennewick, and is now an artist in Seattle. But he's engaging with Hanford aesthetically, okay? And the aesthetic dimension of remembrance may be a component into the deep future. Here's another one of Dykman's reactor pieces. Okay. About 7 more minutes and we'll wrap this up. We're going to get to the burning questions here about what happened after all this stuff. I don't have the answer, but I've got some suggestions. Redox. We're going to hone in on redox here at the end. We're going to finish with redox. No chemical emissions data collected or available. Bruce is nodding. Okay. This is for me, because I'm a lifer. Bruce is a lifer. He's expanded and diversified into way more cooler stuff than me in Europe and all over the place. But for Bruce to say, yeah, Brian, you're right, this has been my guess. So let's follow this up. Does this matter or not? Let's find out. Redox emission sources. The dissolver tanks, maybe, if you're going to turn solid uranium into slurry. Yeah, the stack. Bruce is going to go over that, maybe. Solvent extraction columns, I think so at redox. Others would probably argue against me. They were designed for no leakages. I'm not sure. Process cells, the stack itself, yes. Hexone, oh yes, look at the records. They bought more hexone. It was supposed to be a closed loop system. No, sorry. So question is open there, okay? The data on radiological, it's dialed, okay? It's all there to go ahead and look at it, have the discussion. These are areas I'm interested in because we can't quite get our arms around it right now. Here is where the tire hits the road. This is the open question. Former Hanford worker data. It is based on dosimetry primarily. This is the primary source. The problem with dosimetry data in Hanford worker data is that the dosimetry data exclusively looks at ionizing radiation. These are chemical processing plants, okay? Now, here is where it gets more interesting. Gilbert and Marks. These are some of the most respected, you could argue conservative, occupational epidemiologists ever to write papers. They have, in every paper they've ever written, a footnote or a paragraph, along with, you could call the left side or the right side, or there's a mild disagreement, let's put it that way. They all agree and have a footnote saying, we have zero data on chemical processing emissions. It is likely a confounding variable. This really bothers us. However, here's this paper. Okay? They all say that, every one of them. The papers diverge in their assessment of the causality of excess cancers. Multiple myeloma and pancreatic cancer, they are in excess. In the worker, this is not public, this is worker data, okay? They are in excess. They're in complete agreement on that. However, the ability to exclude these cases because there is no relationship with ionizing radiation, see? So they're able to exclude some excess deaths, all right? However, if we were to look outside Hanford to other industry, what have other people found about pancreatic cancer? It's perniciously really, really hard to figure it out. Really hard, because it is very difficult, and even with a post-mortem, to determine what the origin of a cancer was. You talk to pathologists, it's very difficult, okay? However, certain solvents are definitely connected to an increase, all right? Wrapping up, future research may benefit from further assessment. Bruce, I doubt we'll get the funding for a full chemical. What do you think? Another Hanford dose? Maybe not. I don't think so. It's not going to happen, believe me. However, I'm putting it out there because I'm an independent scholar and I can do that. Connections with Japan, to sum up. Japan has invested significantly in smelting from 56 to 2009, especially Tokai. 45 tons and they used Purex, the same process. I thought that's fascinating myself when I found this. Here's another thing that is a little nugget to consider. The only non-weapons signatory of the Non-Proliferation Treaty to fully recycle and reprocess fuel. And then here's what you really should know about this, if you want to get into the weeds for 30 more seconds. The key point here is that the Japanese plutonium has plutonium-240. It spontaneously fizzles, and fissions, I should say, spontaneously could lead to a weapon that didn't operate fully. And there's your difference between the two. There you go. Thank you.
Maybe a clarification, but
yeah.
Wasn't the use of steam jets was also to not have any moving parts inside those cells, right? To reduce the maintenance needed, because once used, it would be so difficult to get any kind of maintenance work done.
100%.
Especially repair work, that you just had to design something that had as few moving parts as possible.
Absolutely. Absolutely. And if you think back to some of the slides, much of this work in chemical processing dates back to 1880. And that's why I was referencing the other non-ferrous metals plants and in industry. So you had the knowledge base of DuPont in processing for munitions, and the knowledge of chemical engineering was at a very, very high level. And so it's an underplayed story because the bunch of people that were standing around looking at the xenon poisoning and what happened, but you can also look at at B reactor, but you can also look at on the other side of it, chemical processing, the foresight that the chemical engineers had in deploying tried and true technology so that it was as bulletproof as possible. And the steam jet is bulletproof, as well as the other points that you made about maintenance. Of course, that's implicit within that, because if you were to look, the entire apparatus is below a cell, it's below grade, and all the work had to be done remotely with a crane operator. So your point is exactly spot on. Okay. Yeah. The only thing it would depend on, so if we go back to, if we look at, for example, the rail car, I don't know if I can get that slide, but if we get to the rail car, let's take a look here, and I can give you, how about the Warren Dyckman painting? That'll explain it. No, sorry about that. No, sorry. We'll go off of that. We could almost go off here. Let's do that. Let's say that this is the front end right here. Yeah, I'm not sure. I don't believe it. It's possible it would be. There is the rail car. So imagine the reactors along the river. The cask cars are critical because there are a few other ways you could do it, but it's extremely dangerous. The amount of energy coming off of that load is very high, and so they're lead lined, and there's a method for inserting those irradiated rods into the car, and then it would move up onto the plateau to the leg storage building, and that is a critical piece because there is a set of considerations that were inputs for operators there as to the amount of time that they were staged. Then that cask car, the locomotive would be hooked up to it, and depending upon the year you're talking about, if you're talking about 1945, it's going to T plant, pretty likely. If you were talking about the 50s, a lot of it's going to redox, or other plants, but it's kind of a Gantt chart. I mean, they're operating and shutting down, and then when Purex kicks in, most of the whole idea with Purex is that redox used gravity feed for columns, so it was a continuous process, but not, gravity feed. So Purex used pulsed type columns, and that was a continuous process, a real actual workhorse. So if you can imagine going from batch to these crazy columns, that's why redox has the high bay. Inside of that are countercurrent, how oil and water separate. You have an aqueous and organic phase. They, split off. So they would be loaded into redox and start on their journey, after becoming a slurry that way. In Purex, the same case. There was a rail entry point, and that cask car would be opened up, and it would essentially, the irradiated slugs would be, really, you could look at it and say, steam jetted. You could cut out, you really could. At Hanford, centrifuges were absolutely central to that work. There was a lot of work. Many workers just were pros at running centrifuges. These are 100 to 300 gallon centrifuges that are spinning real fast. So there's a lot of work going on there, and there's a lot of work in the concentration, and obviously it's a separate topic to talk about the metallurgy itself, which I'm not discussing right in this talk, but the load out from the processing itself and the concentration of that. So that's really what you're talking about with the cask itself and the movement through. It just would depend on the year you're looking at. And then you would know.
Did the cells leak out?
Yes, they're absolutely. So you had, and you can, if you'd like, you could get a candlelight with me and we can look at the redox flow sheet, and you can look in those cells at how they have the engineers plan to handle that, where that goes, how they handled it. In each case, if you're probably, like it or not, have read or are familiar with the tank system. Whether you might not know it, but there are underground tanks out at Hanford. There's 177 of them. They are totally and completely linked inextricably to chemical processing. Absolutely. Every plant had a tank farm. It's not just a generic tank farm. They are directly connected in piping to each one of the processing facilities. Yeah. Does that answer your question? There isn't, I wish I could, it's just, there are too many permutations of that possibility. If you look, for example, if we were to take on a spreadsheet each of the processing facilities, they each have a different number of cells that are below grade, and each of those cells have a different function. So you'd really have to look at every cell at every plant to look at where the diagram was as to where that actually went to answer it. But you can answer it. Those diagrams are available. So that could be looked at. Absolutely. Yeah. Yes. 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 Yeah. Well, part of that's a really great question, and part of what far be it for me to have the answer to that. But what I do know is that there are some Swedish scholars and a woman at Berkeley named Rosemary Joyce who've done the best work on the future of nuclear waste and how to communicate that. There was the idea of an atomic priesthood. There's a whole set of really out there documents that were published in the 80s that people sometimes reference. There were these two teams. I mean, there was a Harper's article on it, and you can get into that if you want, but what the people have realized is that the big warning marker concepts are a fallacy, because no society has ever had sufficient information at the present time to project out into the long-range future. So the best ideas, I believe, and this is what I'm trying to suggest in my book, is that it's a baton handoff between generations. And that's one of the reasons I think art is important, because artists can keep, along with the great work that Professor Franklin's doing and Professor Bauman and others are doing, that to me is super important, because the diversity of scholarship, the richness of that exclusion, all of that is what is going to keep people engaged to Hanford. The work they're doing, I've been around a long time. It's really groundbreaking, incredible work. You didn't see that a few years ago. You just didn't see it. So, I mean, this is the sort of thing that You can come and listen to a talk and go, this is for real, you know. It's the whole thing. So it's a baton handoff, and it's really a huge open question, because I'll leave it with this. The end game, a lot of people think, people that are doing this for a living and looking at this, is for the Department of Energy to part ways fully and completely. Now, that's been done at most every other site. What you're left with is a set of institutional controls, which is a document that's between 50 to 250 pages that would go to the cities and the counties as to how to handle the site. And that, to me, that's problematic. To me, I think that more is needed than that, but you know, there you go. I want to cut into Bruce here.